In this video, I want to talk about combinations of random variables, and we're going to start by talking about linear combinations of random variables, and then we're going to talk about the specific instance where the random variables we're combining are all normally distributed, because we're going to be able to answer some special kinds of probability questions if all the random variables in the combination are normally distributed. So let's just jump right into it. When we talk about linear combinations of random variables, we're talking about something like this. So let's say that I know on average that I walk 1.1 hours per day. So I could say the mean of my walking time is 1.1. And let's say I also know, because maybe I've collected data for an entire year, and so I have a pretty good idea of both the mean and then also the standard deviation of my walking time is 0.2 hours. Let's say I also know that I spend a certain amount of time biking each day, and the mean of my biking time is 0.6 hours. The standard deviation of my biking time is 0.1 hours. So the point here is that I have two different random variables. A random variable W that models how much time I spend walking each day, and a random variable B that models how much time I spend biking each day. But now I'm interested in my total activity time. I want to know if I add these two together to get total activity time, the time I spend walking and biking combined, how do I use the data that I already have to find totals for activity? Well, for the mean of my activity time, and we'll use the variable A to model total activity time. The mean is really easy. When I want to find the mean of the combination, so the mean of my total activity time, I just add the means together. In other words, when we want to find the mean of the sum, we just find the sum of the means. The standard deviation of the variable A, or my activity time, is not quite as simple. I can't just say the standard deviation of total activity time A is the sum of these two standard deviations. It doesn't work that way. There won't be a true equation. What I have to do instead is first look at the variance. So the variance, remember, is sigma squared. So we'll say the variance of total activity time is going to be equal to, I square the standard deviation for both walking and biking to get the variance for walking and biking, and then I can add the variances together. So I say the variance, sigma squared, of walking plus the variance, sigma squared, of biking. When I add those two together, it is true that that is equal to the variance of total activity. And then from there, to find standard deviation, I simply take the square root of the variance for activity, and I get the standard deviation of activity. So this was mean here, and then this was variance and standard deviation here. Now, similarly, if I want to find the difference of my random variables, for example, I want to subtract biking from walking to find the difference, the same thing here with the mean. Instead of finding the sum, I can find the difference and just subtract. If I want to find the difference in the standard deviation, I still find variance, but the variance is still going to be the sum of the variances, not the difference of the variances, which I know might seem counterintuitive, but it's true. We're going to use the sum both times, and then we still just take the square root of variance to get standard deviation. In other words, if we were to make a table here to describe the formulas that we would use for the sum or difference, we would say that we would have the sum or the difference of two random variables, in our case, W and B, but we would say that the combination would be given by, and we'll use our variables here where the total combined is activity A, and then the difference of the combination is D. So for the sum, total activity will be equal to walking plus biking, but the difference between walking and biking will be walking minus biking. Then for the mean, I can simply say that the mean of total activity is equal to the mean of walking plus the mean of biking. And I can say that the mean of the difference is equal to the mean of walking minus the mean of biking. But for the variance of the sum versus the difference, the variance sigma squared of my total activity is going to be the sum of the variances here for the sum. So we'll say sigma squared for walking plus sigma squared for biking. But then here's where people get thrown off. The variance for the difference is the same thing. So the variance for the difference is still the sum. So the variance for walking still plus the variance for biking. So that is the tricky part to remember right there, that this is still a sum and not a difference. And then for the standard deviation, we still just take the square root of the variance in both cases, and we end up with sigma of A or sigma of D. So these are the formulas that you use to find the mean, variance, and standard deviation of either the sum or the difference of a combination of random variables. Now here's where combinations get really interesting. When both of the original variables, so in this case, the original variables W and B for walking and biking, when both of those are normally distributed, that means that the combination, either the sum or the difference, will also be normally distributed. As long as the original variables are all normally distributed, then the combination will be normally distributed as well, which means that we can do problems like this one. So let's say that we have a popcorn company, and this popcorn company fills tins, metal tins, with varieties of their popcorn flavors. So they have one tin that is filled with 3 flavors. We've got a cheddar popcorn, so maybe a cheddar popcorn in a third of the tin. We have a caramel popcorn in 1/3 of the tin, and then we also have a chocolate popcorn in 1/3 of the tin. So let's pretend that as they're filling these tins, they try to put 1 pound exactly of each flavor of popcorn in the tin. And let's say the amount of each flavor that they put in is normally distributed with a mean of 1 pound and a standard deviation of 0.1 pounds. So let's go ahead and call the cheddar popcorn, let's give that a variable name of D. The caramel popcorn will be M, and the chocolate popcorn will be C. What we're saying then is that the mean of D is 1 pound, and the standard deviation of D is 0.1 pounds. And the same goes for the others. The mean of the caramel popcorn, M, is 1 pound. The standard deviation of the caramel popcorn is 0.1 pounds. And then the mean of the chocolate-covered popcorn is 1 pound. The standard deviation of the chocolate-covered popcorn is 0.1 pounds. And we've been told that all 3 of these variables are normally distributed. If we define a new variable as W, which is the weight of a full tin, a tin that's already been packed with all 3 flavors, then we can ask, what is the probability that a full tin contains less than 3.25 pounds of popcorn? And we can see how that's an interesting probability question because we know that the mean of each flavor is 1 pound. So if when they're packing the tin, they hit it right on the money for each flavor, then they'll have 1 pound of cheddar, 1 pound of caramel, and 1 pound of chocolate, and the tin will be exactly 3 pounds. But sometimes they're going to overpack one flavor a little bit and underpack another flavor a little bit, maybe overpack the other flavor. There's some standard deviation there for each flavor. Sometimes they might overpack the tin enough that it's going to weigh more than 3.25 pounds. In other words, they put more than 0.25 extra pounds in it, or more than a 1/4 pound extra of popcorn. So we want to know the probability that the full tin is less than 3.25 pounds. Well, as we know here from the formulas that we built for these combinations, if we want to find the mean of the total weight, we simply add the means together for the variables that make up the combination. So we can say that since W is equal to D plus M plus C, that the mean of W is equal to the mean of D plus the mean of M plus the mean of C. And then we can substitute those values and get 1 plus 1 plus 1, or 3. So the mean weight of a full tin is going to be 3 pounds. Now we need to find standard deviation. But remember, we can't just add the standard deviations together, even though our linear combination is just adding the 3 variables together. Instead, we need to first find the variance of each of these variables individually. So to find the variance of each variable, we square the standard deviation. So we say the variance of cheddar here is going to be 0.1 squared, which is 0.01. The variance of caramel, we square again the standard deviation, and we get 0.01. And then the variance of chocolate, we square the standard deviation, and we get 0.01. Now, from this, we can find the variance of the total weight. So the variance, sigma squared, of the total weight W is equal to, and here's where we add all 3 variances together. So it's equal to the sum of the variance of the cheddar popcorn and the variance of the caramel popcorn and the variance of the chocolate popcorn. And then we can make substitutions and say 0.01 plus 0.01 plus 0.01 is equal to 0.03. So this is the variance for the total weight. Then to find standard deviation, we just take the square root of both sides. So we say the square root of the variance is equal to the square root of 0.03. And then that gives us a standard deviation of approximately 0.1732. And now that we have a mean and a standard deviation for the combination variable W, we're actually able to answer probability questions, because remember, we said that each of the original 3 variables was normally distributed, which means we know that the combination, the total weight, is also normally distributed. So now we have a normal distribution for W, maybe it looks something like this, and we have a mean here of 3 and a standard deviation of 0.1732. So maybe that comes out to here and here. We would have a standard deviation of 0.1732. So here that would be up at 3.1732. But we've been asked in this question, what's the probability that the tin contains less than 3.25 pounds? So maybe that's somewhere right here, 3.25. We know that it's outside of the first standard deviation because the first standard deviation gets us all the way up to 3.1732. So what we want to do is we want to look at the distance between 3.25, the value we're interested in, and the mean. So we say 3.25 minus the mean of 3 is equal to 0.25. Then we want to express this value that we found in terms of standard deviations. So the way that we do that is we take the 0.25 and we divide that by the standard deviation 0.1732 approximately. The result of that is 1.44. So what that tells us is that 0.25 is about 1.44 standard deviations, or a little less than 1.5 standard deviations away from the mean or above the mean. So what we want to do then is look up 1.44 in a z-table, and when we do that, the value that we find in the z-table is 0.9251. we want to know the probability that the weight is less than 3.25. So we want to know the probability that the weight W falls anywhere in here all the way up to 3.25. Well, this 0.9251 represents all of the area below the 3.25, which means that there is about a 92.5, or maybe we could call it approximately 93% chance that the weight of the popcorn in a full tin is less than 3.25 pounds.